So last week we talked about Chandy Lampert, right? We talked about snapshots, if you remember. And then we talk about the consistent snapshot, Chandy Lampert algorithm for taking a snapshot, how we taking the consistent snapshot. And then we talked about the whole concept of a snapshot, why we're using it, I mean, why it's the purpose of it, and why we need to have that, okay? So we use that Chandy Lampert algorithm for snapshot, right? So today I'm going to talk about this. Basically, you can consider that for correctness, okay? When we be talking about the Chandy Lampert algorithms and like snapshot algorithms, it's mainly for correctness in distributed system. I'm going to talk about this briefly today, and most probably in future classes, we're going to refer to this and talk about it more, okay? But before I start, I just want you to know these definitions, at least, or yeah, let's say definitions, how I'm defining this. Before I continue, the presenting groups are here for today?
Yes.
Okay, perfect. It's Dorle and Alejandra, see?
Yes.
Okay.
We are going to present at the end of the class?
Yeah, that's why I asked actually. Because most probably, let me talk about it. No, but it won't be at the end of the class. It won't be like in 10, 15 minutes, okay? It's fine with you? Okay.
Yes, sure.
So correctness in distribution system can be seen in two different ways, liveliness and safety. So I'm going to talk about each one, liveliness and safety, so it won't be confused with each other. So liveness means guarantee that something good will happen eventually. And so by having this eventually means we are not basically having a time, we are not bounded by the time, okay? So eventually it means like at some point in time, something good will happen at some point. I mean, of course, if you let the system run long enough, something will, something good will happen. So that's basically liveness characteristics of distributed system. So these are some examples for liveness. In real world, you can consider that, for example, considering a sport match, at the end of the sport match, we are going to have a winner. I mean, don't consider those a draw one, okay? At the end of the, for example, 100 meters run in Olympic, we're going to have a winner. We're going to have the first person passing through the line. Or another example can be a criminal will eventually be jailed. That means something good will eventually happen, right? That was the liveliness. Talking about the examples in distributed system, you can consider this that I put here. Distributed, for example, talking about distributed computation, you can guarantee it will terminate. Talking about failure detections, you can consider every failure eventually will be detected in a non-faulty process. And talking about consensus in the distributed system, for example, you can consider all processes eventually decide on a same value. So these are just some example of liveness. And just hold on so far, I mean, don't get confused. And the safety means guaranteeing that something bad will never happen. So any example you can think of in real world?
Maybe, I don't know, but if you have a healthy life, you never will be sick with something like diabetes.
Yeah, it's let's say if you have a healthy lifestyle, you won't get diabetes. You just die at some point. Yeah, that can be example. I put some more example here, like a peace treaty between two nations. provide safety. If they have the peace treaty, war will never happen, or an innocent person will never be jailed. So if you remember the other example, a criminal will eventually be jailed, okay? And here I'm saying an innocent person will never be jailed, because talking about safety, it means something bad will never happen.
But that is not in real life. That is not true in real life. A
Yeah,
lot of innocent persons are jailed.
that's what I'm going to talk actually. Yeah. So about the example in distributed systems, for example, you can say there is no deadlocks in a distributed transaction system. You remember we talked about deadlocks last time, that this process holds this resource, the other process holds the other resource, this process waiting for this process to release this, and this is waiting for this process to release, and the deadlock happens. Or for example, no object is orphan in distributed object systems. You remember one of the things that we were talking last week was the benefits of taking snapshots. We can make sure we get rid of all these orphan objects, the objects that no one is referring to them, there's no pointer to them. Or another example, like for example, accuracy in failure detectors. If there is failure, you can accurately detect it. I mean, if there is any, it definitely will be detected. I'm talking about like consensus. No two processes decide on different values. So if you can basically satisfy this, these are basically safety characteristics of the distributed systems. So we are talking about liveness and safety. So can we guarantee both safety and liveness in a distributed system or in a real life? As Pedro said, it doesn't happen.
No.
So it doesn't happen. So it's the same like with distributed system. It can be difficult, okay, to satisfy both liveness and safety in a asynchronous distributed system. This is very important. I mean, because of being asynchronous, a lot of issues like those things that we say will eventually happen or will never happen. We cannot satisfy both. We can concentrate on one more, or this one or that one, but satisfying both in a asynchronous distributed system is difficult. For example, talking about failure detector, completeness and accuracy cannot both be guaranteed by a failure detector in an asynchronous distributed system. Or consensus, decision and correct decision cannot be both guaranteed by any consensus protocol in an asynchronous distributed system. So I'm saying this, but if, for example, we cannot guarantee these things, so how we are even using the distributed system then? What do you think? I mean, I'm not tricking you. We cannot really guarantee them, okay? We cannot guarantee both. It would be very difficult, or let's say we cannot do that. But still, I mean, we're working on using a distributed system without any sensible or any tangible problems, okay? So, of course, we're going to have issues in talking about consensus. We're going to have a disagreement about the value of an object or the decision between different computers, but we're going to somehow deal with those situations. Or about failure detector, at some point there would be a failure that we might not detect it, and it can cause some issue later, okay, about the consistency of the data, but later we have to deal with those type of situations. It will happen, but then we're dealing with it somehow. So these are like an example in distributed system, as Pedro said. In a real life, no legal system, no matter where in the world, cannot guarantee that all criminals are jailed, or no innocent person goes to jail, right? I mean, we cannot guarantee this. So we cannot guarantee both at the same time. At some point, some innocent will be jailed. At some point, some criminals will escape the judgment, how to say, the crime. Okay, they get away with it. A lot of times they get away with it. So these things happens. So just remember these things. We're going to refer to these things. I mean, it's not you think there is something complicated here, we're going to refer to this in next classes. I just wanted to mention it here. And then we can talk about today's class, okay? Talking about eventual consistency, or we're going to talk about bio. So it's the same thing that group 3 going to talk about. So I'm not going to talk about it much. I'm going to just prepare you, like giving you a little bit background. Then they're going to talk about it. And if there was something missing, then I'm going to cover it, okay? So basically, that's the idea. Oh. So the whole idea today is about this word, about the consistency, and the important thing is eventual consistency. And basically the paper is bio. So we want to talk about consistency. So we want to avoid this type of silly issues or excuses, okay? We want to make sure if we have different or replicated databases, like the example that I was talking about, the banking things from the first week, banks like in New York, in San Francisco, we have these replicated databases that are physically in different locations, and we want to have a consistent data. So before I start talking about that, I want to talk about the CAP theorem. And what does the CAP theorem says? It's basically a theorem in distributed system, and they say it can be broken. Basically, CAP stands for consistency, availability, and partition tolerance in distributed system. Consistency means all clients see the same view of data, even after update or delete. I mean, they are very sensible, tangible. I mean, don't afraid of it. Okay, so data should be consistent. If you have a replicated database, we want all the data to be consistent. Your bank account in this server and another server in different parts of the world, you want it to be consistent. Availability means all clients can find a replica of data even in case of partial node failure. Okay, so we know the node failure can happen. We are totally relying on the network, and we know the network is not 100% reliable. Okay, so the problem happens. Some server is going to get out of service. Some how to say, the network at some point can be partitioned. One server can get out of service and get disconnected from the rest of the network. So we want to satisfy this availability. So there are basically the characteristics that we need to satisfy in distributed systems. Here are all distributed system characteristics that we need to satisfy. Okay. And partition tolerance means the system continues to work as expected, even in the presence of partial network failure. Okay, so network should work. I mean, the system should continue working. The data should be available, and it should be consistent. Any questions about this? So this is the CAP theorem, and what the CAP theorem says. For example, the CAP theorem says you cannot satisfy all three at the same time. Okay, that CAP theorem's the whole idea, and they say it's a theorem that you cannot break it in a distributed system. And we're getting close to not to breaking it, but to perfecting it. Okay, that's why you never feel any of your data is missing. If you have constant internet connection, your data, you feel, I mean, at least the feeling that you have is 100% of the time that your data is available. Okay, that's at least the feeling you get. It's not the real things, okay, but that's the feeling you get, that it's partition tolerance, it's available and consistent. There's no issue. But in reality, it's really hard to satisfy all three at the same time, or what they say is like impossible. Okay. So at some point we should choose which one we want to do. If we want to have like a consistency availability, we want to have consistency partitioning, or we want to have like availability partitioning. Which one we want to satisfy, and which one we want to sacrifice. But if you look at it more carefully and think about it, one of them you cannot ignore because that characteristic is deep into the distributed system that you cannot just ignore it. Any idea which one is it?
The consistency?
Partitioning.
Consistency.
Partitioning. Jose was right. Jose Antonio. I mean, this you can't ignore. You cannot say, okay, I just want to basically go for CP or AP. Okay. What I say is like, because this happens. Okay, this is by default will happen. Because again, I'm saying like network is the base of the distributed system, and we know it's can be broken, can be down at sometimes, okay, can be partitioned. So your distributed system should be partition tolerant. I mean, no doubt about it. This should be for sure satisfied. Your distributed system should be partitioning. I mean, of course, you may come up and think about something that does not, okay, require this, but most of the thing we discussed, partition is part of it, okay? So then our choice will be either we want to sacrifice consistency or we want to sacrifice availability. This should be satisfied, okay?
But shouldn't be consistency more important than partitioning? I mean, for example, in the bank example that you already said, imagine that someone is retiring or getting $1 million, and then the system is not updated and can again retire
Okay.
$1 million.
So
Yeah, I got it. Maybe I'm explaining it bad. You cannot have consistency without being partition tolerant.
Yeah, because
you cannot-
consistency, sorry.
Pardon?
Yeah, because consistency could be in either both ways. You could be consistent being bad, or you can be consistent being good. That means the system can be consistent being bad if, you know, one of the other, at least partitioning doesn't comply.
Yeah, I would say like you cannot have the consistency if your system is not partition tolerant. Oh, you want to add something?
Actually, like I only wanted to mention, like, for example, between consistency, availability, and partitioning, like all the systems we have it like at some proportion, but depending on the system, on the application that we want to develop, let's call it like that, we can select different like modules or libraries that, for example, some of them are more consistent and are more on the CP side, consistent and partitioning. Some others are more highly available and fault tolerant. It's called usually partitioning. And also some others are consistent and available. It depends also on the type of application, right? Because, for example, sometimes like in Facebook, you don't care in some part of consistency because, like, for example, for displaying information in the wall, you don't care if you always display the information always in the same order, right? Or if some like publications are missing or something like that. So depending on the application, it's like which system you're using, but gathering the three of them, like most, at least with the 99.99% of accuracy, it's really difficult to achieve, right?
Yeah, exactly.
So I only wanted to mention that these three descriptions, mostly this, well, you usually mentioned like, it's consistent because 99.99% of the cases, you always get like the same type of, well, you get consistent data, right? But it doesn't mean like that it's always like in the 100%. Does it make sense?
Yeah, for me too. Yeah. Yeah, thank you, Paul, for your comments. Yeah, it's true. I mean, as he said, I mean, you sometimes, as like you Paul said, like Facebook posts, right? Consistency doesn't really matter there. Not, for example, all friends can see your posts in the same particular order. I mean, it's not gonna change much things, okay? So I mean, depend again on the application, it can varies the importance. So for example, talking about these things and consistency, availability, partition tolerance in a database, you can say, for example, Oracle, SQL Server, MySQL, they sit here, okay? They are consistent and they're available databases, but they are not partition tolerant. Like MongoDB, Redis, I'm not that familiar with, for example, Redis here. I'm familiar with this one, not with Redis much. So if I'm making mistake here, really correct me. For example, MongoDB and Redis, they are partition tolerant, consistent, but not available. Not 100% available. Okay, they are sacrificing availability, not like ignoring it totally, sacrificing availability more for consistency. Or like Cassandra and CouchDB, they are more like sacrificing consistency for availability and being partition tolerant. Okay. So having that in mind, let's talk about today's topic. Today's topic is about eventual consistency, right? We're going to talk about consistency, but eventual consistency, not a strong consistency. We want to eventually reach a consistent replicated database. So let's do a quick recap about what we discussed last time. So you remember we talked about totally ordered multicast. So the goal was all side applies update in the same Lamport clock order. You remember the issue that we were talking about, the banking, different bank basically in different locations, physical locations. So client send updates to one replica, side J, and replica assign its Lamport timestamps. I'm going to go quickly because we talked about it just to review it. So the key idea was here to place event in a sorted local queue, right? If you remember, we had a sorted local queue, and we sorted by the increasing Lamport timestamps. We used the Lamport timestamps in order to make sure we are sorting all the events. And then, if you remember the process, you were saying on receiving an update from client, broadcast it to others. On receiving or processing an update, add it to your local queue, okay, and broadcast an acknowledge message to every replica only from the head of the queue. On receiving an acknowledgement, mark corresponding update acknowledged in your queue, and remove the process that basically that everyone acknowledged from the head of the queue. If you remember, we talked about this example, paying the percentage to an account and also adding some money to it. So we had two replica P1, P2. So this is the message from P1 to P2, P2 to P1. They have their local sort queue. The percentage message arrives here, and it will be in the queue. This one will arrive here. It will be sorted because they have the Lamport timestamps. So the P2 receives this. It's in the head of the queue, acknowledged, okay, from the head of queue, and start processing the command, let's say, and then P1 receive acknowledgement from P2 and start processing it, and P2 acknowledge it, and then they process it. Remember? So this was totally ordered multicast that we talked about. And then that day we talked about, are we done? And we said, not by a long shot, because we assume no node failure, no message loss, and no message corruption. That was the assumption that we simplified it. So we want to talk maybe a little bit more about this part. So considering availability versus consistency, because we already said that the distributed system should be partition tolerant. If you're having an application in the distributed system, partition tolerance should be there. So we know the totally ordered multicast kept replica consistent, but had a single point of failure. If you remember, we discussed that how all the replicas know that all the messages are message messages are acknowledged by everyone from the basically a central server. That was what we discussed about the totally ordered multicast. So it has a single point of failure. If the server fails, the central server, then everything will be broken down, all the systems. So it's not available under the failure. So just remember, I'm going to talk about, today we're going to talk about eventual consistency. We are not going to talk about a strong consistency like each have operation in the same orders everywhere and strong with a strong reachability. We're not going to talk about it. We're going to cover this later. But what we're going to talk about this is if the network fails, which is a common case, can we provide a consistency when we replicate? So that's the question we're trying to answer today, talking about the eventual consistency. We want to say, basically, they're going to talk about Dorle and Alejandra, they're going to talk about eventual consistency or bio. So what it means, eventual consistency, again, we have this word eventual. It means we are not bounded by the time. Okay, eventually we arrive to consistency. So it means if no new updates to the object, eventually all reads will return the last update value. So it's very common that we use eventual consistency, and we're going to talk about it why. For example, consider Git, iPhone Syncs, Dropbox, Amazon Dynamo, they're all using sort of eventual consistency. Eventually your data will be consistent. And why it's important for us to have eventual consistency? Because we want fast read write on a local copy of data, okay? I have my local files in my laptops, in my Dropbox, okay? I want to be able to write and read from those data fast, okay? And also, which is another point which is very important is about disconnected operations, okay? Not always my laptop is connected to the internet. Let's say, I mean, now, okay, this time that we are living is still internet not is available in all the flights, okay? Just some example, okay? So I'm having flight, short trips, okay? I'm not that rich to buy data on the fly, so I'm trying to just edit some documents. Still, I'm working on my document. I'm editing the paper and I'm collaborating with other people. So I'm having this disconnected operation. I'm updating my information, right? I'm updating the data. So those are important. But then I'm updating this file, okay? Imagine these are real, real case, it's not an imaginary thing, right? I'm updating this, I don't have internet connection, I'm updating a file that is in a shared folder with my friend who is sitting in Japan, and we are editing this article together. I go to the airplane, I lost connection, I start updating this file. Then when I get connected, it will want to sync with the information, right? And the folder is in my computer, is in cloud, my friends or my colleague in another part of the world. So we can have this issue, which is conflict rights, okay, to different copies and how we can reconcile them. Maybe I edit one part, and when it gets synchronized, Dropbox realized that paragraph was deleted by my colleague in Japan because he thought we don't need to have that, okay? So now we have two conflict rights. I did something, he did something, now we want to synchronize, and these two files are conflicting. So how we can come up, how we can solve those type of issues. So that's why we're going to talk about bio, weekly reconnected, weekly, okay, it's not like week, okay, I don't know how to say it, weekly connected replicated storage systems. So the example, I guess they're going to talk also is about meeting room calendars applications, okay, that different people wants to, just imagine about this scenario, different people wants to book a room in a meeting room, let's say in tech, okay. So different people want to basically book their rooms, and we want to avoid this type of issues. For example, overbooking the rooms at the same time by different peoples, or for example, resource not utilizing all the resources that we have. For example, by mistake we missed to book one rooms and we are fighting about another room because the data are not consistent. But we want basically everyone to see the same set of entries eventually in the calendar or in the book data for that room, particular room that we are fighting for. So eventually we want to see that everyone see the same calendar. I don't want me booking the same room and another colleagues booking the same room. So the paper is written in 1995, right? Carla, Alejandro, do you remember?
Yeah. 1994, and actually I think you are doing my presentation.
No, that's exactly where I'm going to stop. Okay, I don't want to spoil that. I'm just giving the background. So the context of the paper is like 90s. Okay, 1994 exactly. So it's a dawn of PDAs, laptops. Okay, hardware is clunky, but showing clear potential. So I mean, imagine we are living in that time. Okay, it's just PDAs are coming up. We have been basically clunky hardwares, but showing high potentials. Okay, so we have these commercial devices that do not have wireless connections all the times, and we don't have internet connection constantly all the times, like we do almost nowadays. Still, we don't have that 100% of the time, but almost we are getting there. But the problem is still didn't go away. The devices might be off. You might not have network access. Okay, and local reads and writes are still much faster than working with the cloud. Okay, still it's much more faster. I edit my not much like very much like much faster. Okay, not that much faster, but still it's much faster if I edit or read documents on my personal laptop than getting it from the cloud in my browser and working on it. So these problems has not gone away. Okay, so still we are dealing with it. That's why eventual consistency is important. So I'm going to let me see what I have here. Okay, so I'm going to stop here and they're going to take over. Okay, so I just wanted to give you the background. Okay, you won't be mad at me. I just wanted to give you the background and a little bit like reminder of what we discussed, talking about consistency, its importance, and why you should know and discuss about eventual consistency. Okay, or if you want to take like a 8 minutes break, then they start, because after they start, we're going to have air talk, discussion, question and answer, and so on. So let's come back 7:35. Okay.
Okay.
Yep.
Okay.
Professor?
Sure. Yes.
Yes, Marco. Just wanted to ask if it is enough to have that you invited us to the organization for the Git review, or well, I'm not sure if we did it well.
Let me check.
Ours is group 2.
I think you're here, but what I want you to create a repository in this organization and then push your updates to this repository. So the whole idea is so I can have a copy in this organization of
Okay.
your work.
So it's not like we have our own, right? I mean, I copied to my own workspace, but
you can. I think you can clone that here.
okay.
You can do that. Okay.
All right, yeah.
just rename it like this, so I know this repository belongs to this group, and that's belongs to this group.
Okay, yeah, got it. Thank you.
So the whole, it's maybe a little more too much complication for having a copy of your repository, but I just,
Yeah,
my
okay.
knowledge on GitHub is limited, so.
Yeah, mine too. Yeah. Okay, thank you.
I'm here if anyone has questions. Doubt.
So we are going to start.
Okay.
Okay, so
Please, before you start, guys, please pay attention because what they're covering, I'm not going to cover again. If there was any missing things, then I can talk about it, but I see they talk about it, then it just pass. So that's the only time we're going to hear about Bayou. Please go on.
Okay, so today we are going to talk about Bayou. So what is Bayou? As the professor told us, Bayou is a storage system that was created in 1994 and was created for mobile computer environments and portable computers. As I told you, this system was created in 1994. So have in mind that in that time, the connection was very expensive and Wi-Fi wasn't available in all the places as today. And this will help us to understand how distributed systems are built today. These systems support collaborative applications that do updates that are not in real time. And which kind of applications? Applications like as we use today, like mail, calendars, bibliography databases. So the question they asked to themselves when they built this system was, how do we build a system that allows update anywhere with concurrent with connectivity and have a consistent data of replicas? So Bayou system have two goals. The first one that, as I told you, handle frequency disconnections because as I told you, that be connected all the time was very expensive. And the other one is to detection and resolution of conflicts that arise in a system and make sure that all the replicas have the same data at the end. So I'm going to tell you a little bit about the basic architecture of Bayou system. The first one is that this system uses anti-entropy. This means that all the servers are going to compare its data, and at the end, they are going to have the newest data in each server. The second one is that you can do updates anywhere. You can, for example, you don't have to be connected all the time with the same server. You can be connected to different servers each time. And all the applications of Bayou run as clients with the Bayou API. And this system has two basic operations. The first one that it's write, where you can insert, delete, or modify data. And the second one that it's read. So how about you solve conflicts? So for example, let's say that you are doing an update in an application that you want to do a reservation in a meeting room. And you insert, and you do an update, you do a reservation in the time and in the day and in the same meeting room as other person that already did that reservation. So there will be a conflict. So the way that Bayou solve these conflicts are with the rights, that all rights have three components. The first one, that is the update function, that is the actual right. It means that, for example, in this example, our update function is the time, the meeting room, and the date that you want to do the reservation. And then we have the dependency checks that are the ones that do the conflict detection. The way that it works, it's a query that it's comparing with the data of the server. And at the moment that it do the compare, if that reservation, for example, is empty, you are going to receive you are going to do the update, and if it's not empty, you are going to receive a conflict. And then are the merge procedures that are the ones that do the conflict resolution. I mean, like, for example, if you see this code, we have the right over here, and you will see that we have the update here. You are saying that you want to do a reservation in the budget meeting, the 18th of December in 95, and you want to do it at 1:30 p.m. But let's say that dependency check will take a look and say that, oh, okay, this meeting is already reserved or not. If it's reserved, then it's going to do the merge procedure, and it will give you some options like, okay, we don't have this meeting room at that time, but we have another meeting room in that time. So to simplify this code, the way it works is if dependency check passes, then it will be applied the update function. If not, it will be applied the merge procedures. So for example, I'm going to give you another example of which conflicts they were arising at that moment before the Bayou system. So let's say that Juanito have a balance here of $110, and he wants to send, do a transfer to Maria. And then he will do the update, and his update is going to be in the server, and this server is going to send the updates to the other servers. But let's say that this server where Maria is connected don't receive that update. So there will be a conflict because Maria doesn't have already the balance, the actual balance that Juanito have over here. That is that Maria already have the $110. So let's say that Maria wants to do that transfer to Pedro, but as I told you, it will be a conflict because Maria doesn't have the balance already. So how do we know all servers eventually are going to agree? So but you have two features. The first one, that it's all rights processed in the same order in all servers, and conflict and merge procedures are solved in the same way in all the servers. But how about you achieve this consistent replica? Okay, the way that you resolve these kind of conflicts are with the stable rights. But how do we know when a right is stable? So let's say that all the servers had a clock, and at the moment when they receive the update, the server will set a timestamp to the server. And for example, let's say that you have all these rights, all these updates with different timestamps. So all these values are going to be passed to all the servers during the anti-entropy. And then we are the server is going to order all these timestamps in the order that they have to be. But who is the responsible to order all these rights with all these timestamps? So but you have one server that is the master, and is the one that it's going to be all this, or that it's going to do all this order. So for example, we have here our server that is the master, and let's say that you already have your rights and you already have all the timestamps in each right. So we have some rights that are already commit. Let's say that you have this update, and then and it's already a commit, as I told you. And then this master is going to send the right in the same order to all the servers. And then you will have another update here, and you are going to send in the same order to all the servers. But let's say that this guy, Juanito, it's not connected, but there will be, you won't have any issue here, because at the time when Juanito connects to the server, he will receive all the rights in the same order. So, Dorle. Dorle.
I think she's in mute.
Can you hear me? Can you hear me?
Yeah.
Yes.
Sorry. As Alejandra mentioned, biosystem has a large architecture, but one important point to take account here is the storage system implementation issues. And what is that? Well, keep in mind that our implementation is factoring into three main components that you can see on the image that I'm presenting. That is the write log, the tuple store, and the undo log. The write log contains the writes that have been received by a server. It is sorted by their global commitment or tentative order. In this case, my pointer is not working, but you can see in the middle the write log that is yeah. Thank you, Alejandra. And it is divided in the tentative and in commitment. Okay. The other main component is the server tuple store. It is basically a database that is and this is generated by execute the writes in order to process the reads request. It's where you can take consult your information. The undownload, it is helping to rolling back and tentative writes, because when, as Alejandra mentioned, when you do a write to the write log, it is positionally in a tentative site. And after the merge and after the actualization, after that, it will be considered a commitment. Okay. After that, the write log conceptually contains all the writes received by the server, as Alejandra mentioned. Each server must keep track of which writes it have received, but are no longer explicitly in the writes logs. But why? Well, this is ensuring that the servers doesn't accept the same writes from another server during the anti-entropy. Each server maintains a timestamp vector that is named O vector. I don't know if you can see the vector of the write log, that is O. That's vector. Thank you, Alejandra. This is indicating a compact way that the tuple or the message that you are writing is omitted. Basically, the O vector records for each server the timestamp of the latest write from a given server that has been discarded. The next important thing to mention here are the, no, can you go back? Okay. The other important thing to mention here are the timestamp vectors, that is the vector C and the vector F. Those are doing a monitoring of the state of the tuple store. After executing the latest commitment write in the write log. That is the current tuple store. Check that these timestamp vectors are not used for conflict or detention. They are only enabling the server pairs because the server is working on pairs to data, trying to identify the states of writes that need to be changed during the anti-entropy. Okay, can you go to the other? Okay, thank you. And how to apply the set of a U write to the database? Okay, keep in mind that the undo logs permit a server to undo any effects on the tuple store of the write performer after a given position if it is received via anti-entropy. After that, a server intends to insert into insert into a write log. Now the commitment write are inserted on the following the current set of commitment writes, better known to the server. As you can see in this code, it is showing that it is showing how the write log is working. For example, you can receive a write from the client and a write from a server. When you receive a write for a client, as you can see, well, each client has a ID identifier to try to see who is the person that is updating the database. After that, you can see the write state that is tentative, because as I mentioned, when you write, it doesn't update the server automatically. And the other option is when a server is writing information to another server. This is during the anti-entropy. In this case, each server also has the identifier trying to get information and do not duplicate information for another servers with the O vector or with the O vector. Can you go to the other slide? Okay. Other interesting thing to keep in mind of Bayou is the access control, because Bayou, the Bayou design cannot rely on the online trusted authentication server to establish a secure channel, and how the servers know that the user that is trying to use the server is not a virus or is not a person trying to hack all the information. As an example of this, suppose that you user are suppose that two users holding Bayou replicas on their laptops or wherever server that you are using and in a meeting together. Before performing the anti-entropy, each of two mutually suspicious servers must verify that the other has access to manage or use the data. Similar to this, if one system wants to act or do something in a different server, or take information stored on a different server, it will want to make sure that the server has permissions and access, and then must provide that it is authorized to access to that data. A user may be granted to read and write permissions and data collection. For this reason, Bayou system storage is using three different nomenclatures. That is the AC, that is when something has all the permissions, all the access to read and write. The D is permission for user and R are permission for user. D is for read, no, R is for read and D is for manage data. Can you go to the other slide? Okay. Here, Bayou system is comparing the status experience. In this case, the things to remark here is that Bayou system has two important things. That is the client stop work and server work. Is the functionality how Bayou is working. The client stop is a routine library linked into applications that use Bayou for storage management. The servers, that is another one, implements the Bayou storage management, including the mechanisms for conflict detentions and resolutions, server-to-server communications, and persistent database management. here I'm showing a table that has, for example, you can see the server to use for the first one example is a Sun Spark, and the client is using the same server. In the second example, is a server using a Gateway Liberty, and the client is using the same server. But the third option is the server is using a Sun Spark, and the client is using a different server, that is the Gateway Liberty. Also, the table is comparing when read and write, when you only are reading one tuple, and also when you are reading 100 tuples. As you can see, if the server and the client is using the same, that is the Sun Spark, the time that is taken to do that action is for 27 milliseconds. The number that is in parentheses is the standard deviation, because they in the paper are doing a comparison between data, but it doesn't care here. And also in the write, it is considering when the server has conflict and when the server doesn't have a conflict. In this case, all very similar are the functionality and behavior depends of the hardware that you the hardware that the client is using. Can you go to the other slide? Okay, as a conclusion of here, I know that it's a complicated data, and I know that at the end it sounds complicated. It was complicated for me too. And as a conclusion, the main important thing that has this paper is that Bayou as a replicated weakly consistent storage system designed for mobile computing that includes a portal machine with less than ideal network connectivity. Because keep in mind that 20 years ago, the network was different than now. The bio management of the conflict different form on this competency in these following main areas that all those areas are commented in this presentation. That is the non-transparency, pair-wide conflict resolvers, partial and multi-object updates, tentative and stable resolution, and also that is important, the security. And how now how it is working. Can you go to the next slide, please, Alejandra? Okay, now Bayou is still working, and the performance and overhead is acceptable. And Bayou servers and application on today's laptop computers is reasonable comparing with other servers that are using the same behavior, that are Oracle and Coda. And if you want to see something else about Bayou, or if you need a system storage with that characteristics, you can visit the page that is in that link. And that's all.
Thank you, Lourdes. Alejandra. Questions from?
I have one question.
Yeah.
When a client is trying to make a write, and it's, I mean, every time it tries to make it right, does it have to check back with the master if there's a conflict?
Yes, the master is in charge of do the last commitment. For example, you can write something, it is located in the write log, like a tentative, and all the system will be programmed for a time to say, okay, every day at, I don't know, 9 p.m., your system will be updated, and the thing that is in charge of do that updated is the master.
Okay.
Okay, I have another question. This is related to the merge procedure. How the merge, when we have a merge conflict, how the merge conflict is solved?
It is, oh, go ahead, Alejandra. You want to talk?
It's like I told you, like the merge procedure, it's the one that it's in charge, like giving you options. For example, well, the dependency check tell you that if there is a conflict or not. If when you do the comparison, it will return an empty set. If there is another, if there is another update as the one that you did. And if not, there will be a conflict. And there, the merge procedure, I don't know how to exactly tell you how this conflict is going to be the solution, because it depends on the application. But let's say that the merge procedure is the one that it will give you options. Like the example, like I told you, like if you want to do a reservation in a meeting room that it's already reserved, it's already reserved. This is the merge procedure is going to give you, okay, no, we have a conflict here, but I can give you these other options, like another meetings, another time, in another day. I don't know if I answered your question.
Well, what I was thinking is that maybe it's based on time.
No.
No,
No,
because
remember,
you said that when you send a request, you are sending also the time when the process was done, right? Because I saw that also in the procedure, there is at the end a logical clock that you are updating.
Well, it depends. Go ahead, Dorothy.
okay, keep in mind that this system storage is 20 years ago, and the connectivity, it is used when the connectivity is weekly. I mean, for example, you can try, as Alejandra mentioned, to do a reservation. Okay, I want to on Monday from this hour to this hour my reservation, but you need to wait to receive a message that is okay for your reservation is in the your reservation is done in the time that you are specifying here. Is keep in mind that it's not on time. You need to wait to transmit the message to the server, and after your chain is like in the tentative mode, and after that it is commitment, and after it returns the message doing your action.
Okay, I was just asking because, I mean, when you have when you already have in this case the meeting, and a new request is arrive, I think that is not a big problem. You can resolve that. But what I was asking is the problem is when both two persons try to do the reservation at the same time.
Yeah, let's say that you have two reservations at the same time, but it's not the same time because
it's not the same time.
Because the server at the time when it received that date, it will set that timestamp. And I don't know, it's like, I don't know how to tell, like milliseconds, but they will never be at the same time. There will be always like one lowest timestamp and then the other one. I think there's no case that there will be at that exactly timestamp.
Okay.
The timestamp is coming from the clients, or it's coming, who is generating the timestamp that is traveling with the message?
Wait, can you repeat the question?
Yeah.
Yeah, who is generating, or what node is generating the timestamp, the clients or the servers?
No,
The server. The server.
Yes, it's the server at the moment that it received the write. At that moment, the server is going to assign that time. You can that all the servers can assign that time. Not only not yeah, that all the servers can assign that time, but the only server that is going to order all these writes
More questions?
I have one question.
Go ahead.
Imagine two people are offline and they want to schedule for the same Friday at the same time. But who gets the reservation? The one that schedules first or the one that gets connection or network availability first?
I think that the one that it's connected, because you can send the write until you are connected. I mean,
Yeah,
like
but the timestamp it's going to be different, right? The one that is not connected, we will have a early timestamp.
you can receive a timestamp until you are until you do the write and you are connected.
Keep in mind this. For example, what if I'm working, like Kristen is mentioned, in a stub mode, and I want a reservation for tomorrow, but I don't have access to a network, and I never had access to the network, and I arrived to my reservation, and what happened? What happened is something else has or did the reservation. It is, as Alejandra mentioned, it is the first person that has a connectivity to the server is the person that has the reservation. I don't know if I answered your question.
Your application in your mobile, and you have a copy of all the data in your mobile, but then you get disconnected, and then you will do, I don't know, any change on your application, but at the moment that you do the write, you have to be connected, and then your application, but before you do the write, your application will do the update of the data that it's on the server that you are connected.
Okay. Yep. Thanks.
Okay, thank you. No more questions. I'm glad seeing like there's a lot of question about timestamps. That means we did good the first 2-3 weeks. I mean, talking about the time is important.
I have a quick question.
Go ahead.
Can you please repeat the meaning of the letters A, C, D, and R? I mean, the meaning of those, I just forgot it. Please.
From what? Sorry, can you repeat, please?
Yeah, there was one section in the slide where you were explaining about some capital letters.
The types of certificates, right?
Yeah, the
A, C, D, R.
Those. Yes, please.
Okay. I don't remember the meaning exactly. I mean, what is A, what is C? But the first one that is AC is for I forgot the word. Like a private, no, like when you have all access, the full access to the information, to the modify, to read, to write, to the people who manage the server, and
full privileges, you meant to say?
To what?
Yes.
When you have full privileges.
Yes, privilege. Yes, that's the word. And one of the read and the write on data collection for D to the user who the public key is PU. PU is for public user, And the AC is when certificates when are signed. I don't remember the word of this, but the two last one is for access for users. PU is for public user. PU is for public user. C is for encoding access for certificate, and I don't remember what the meaning of PE.
It's okay, just a general idea of what they do with those. That's it.
I'm pasting to everyone the definitions. I didn't remember honestly, so I had to check the paper. So I'm putting it here in the chat.
Oh, thank you, Professor.
No problem.
Thank you.
Okay. Thank you guys for the presentation. I know it was tough because it was new again and I didn't talk about it much. So let me, I'm going to talk about some stuff, and meanwhile, you can do this. And we didn't do this for the last presentation by Fernanda and Ivan. I consider it like 5 out of 5. Okay, Fernanda. Okay, I just forgot last time we do this. Can you see my screen?
Yeah.
This is screen or
yes.
this screen you see?
What was the presentation? Sorry.
This is for today presentation, not for last presentation.
Okay.
Oh, okay. Today.
Yeah, I consider it like full grade for last presentation because we forgot. So.
Do you want us to do it now?
Yes, please grade the today presentation.
But it says group 2.
Oh, pardon. Right.
Yeah, that was my.
yeah. My mistake. So what I wanted to share with you. And meanwhile, I mean, while you're doing this, I want to ask questions to and see. Paul, you're here? Paul? We don't hear you if you're here.
Can I see again the code?
Yep, this one? No, this one.
Can you hear me?
Okay.
Yeah, that one.
So this is the code. I put the code. No, Paul, for you, there is a questions, okay?
Boo.
So what was the problem being solved?
What is the what?
What was the problem being solved by this paper?
Yeah, well, the topic is, since it's eventual consistency, the problem is when some devices have like low, bad connection, for example, if they get disconnected, how to communicate, how to have consistency after a reconnect into the system and have a correctness of data.
Perfect. Thank you. Also, Antonio Rivera. You here? No? Jose Antonio? No. We go with another one. This is the voting. Okay, perfect. We have everyone. Okay.
I win.
You win one time. Okay, the next question is like, just this one. The main, not for you, Dorla, for the next students, about the main. Ricardo, Arturo?
Yeah.
I was excited to answer.
Yeah, come on, Dole, help me out.
Just the main technique, because I think that was a little bit confusing. I want to see if it was clear for you. What was the main technique?
Okay, so what I understood is that when a user, but the client in this case, requests for some changes in the server, they have this kind of request set as tentative, and once they have the connection with the main server, they have like different mechanisms to know if there's a conflict between another clients. So there is a way where they know if there is a conflict, they go through the specific conflict resolution, and if not, they just go with the update part where they just let's say log this request. So in the case there's a merge conflict, there's some specific scenarios where they, I think there's a specific for the request, but in one of the examples was that they gave us this kind of other options where you can also have like this request for another tentative scenario. So this is like the main thing that I understand. There's like two techniques. One for a request for a tentative request, another one that is differentiates if there is a conflict or not.
Okay, thank you. Yeah, almost correct. Okay. Good. I mean, we have 24 votes. I mean, Dorle and Alejandro, you voted yourself too. It's fine. Okay, the main technique, I would say, just to simplify and maybe clear some doubts here, the main technique is having the rights as tentative till you confirm them. First thing. And second thing, I mean, all those questions about time clock, I don't know why Alejandro and Dorle, they didn't refer to the logical clock, Lamport logical clock. That's how you get, I mean, it's not about that you don't get two exactly at the same time, but it's about how you can totally sort all those rights at the end, right? Even if they are the same. Go ahead, Alejandro. You have, I thought you want to say something. But that's the idea. I mean, at the end, we already talk about that totally sorting all the events by using the Lamport clock, by using the logical clock. That's how we basically solve. I just checked the paper to make sure it's not just what I remember, but it's mentioned here. For example, if you look at this, you have the logical clock, okay? So that's what they're using. And if you go to the reference, they are referring to the Lamport paper. So that's how all they can order all the events. The ordering is not an issue, okay? So about all those scenarios that you were thinking about, this one connected, this one first, this one last. I mean, as long as basically you have that timestamp, okay, and the timestamp will be ordered by that primary basically replica at some point, or the server to send the main server. It will be, all those issues will be solved. So so just that one point. I'm going to go through my slide and say some of the points, okay, that I think can be mentioned. I'm just going to fast, please be patient. Okay, I'll just stop in some of them and talk about it. So I already talked about the background. just these are the why. I mean, the whole about the concept of the paper. There was some question about how you resolve the conflict that's at the end, right? There would be some conflict and how you can solve them. They already talk about solving the conflict, but at some point it comes to the application, how the application is dealing with. So the conflict resolution can be application specific. I'm just want to show you one thing that I find in my Dropbox, just to show you how Dropbox is dealing. Anyone has ever seen any conflict in Dropbox? I don't know if you're using it.
No.
No?
But I have seen a lot of Git.
Yeah, okay, I don't know, really, I'm not using Git, so I don't know how Git is dealing with that. But I want to show you the Dropbox one.
Well, Git can be, you can set by default that you want their changes or your changes, and also you can set like a manual resolve conflict.
I see. So yeah, that's, for example, that's the way Git deals with it. So I just searched conflicts and I find this folder. This is when I was applying for SNE. So you can see there I have two folders like this one and this one. And here it says like Unicode encoding conflicts. And if I go inside, you can see both files are like edited at the same time, like this one with this one. But I know why it's happened, because I use my laptop and I use my work, and those times that I was separating. Okay, in my home I use maybe have my like Persian alphabet also in my keywords, so that might be making some issue when I was editing this particular file, and when it starts syncing with my, I don't know, for any reason, with my other Dropbox, which is in my work laptop, the shared folder that I have there about tech. So I started having this conflict copy here. So at some point, what all I'm trying to say, at some point, it comes to the how application is going to deal, because some of the issues or some sort of conflict might not be that easy to solve. So for example, in this case, Dropbox decided to keep both copy and let me decide for it. What I want to do with it, okay? Because it's not so clear for Dropbox how you can deal with it, how it can deal with this type of solution conflict. We already talked about. Another thing is this one. I mean, that's what I said. You want, at the end, you want to have the total ordering of all the updates, okay? And that's why they mentioned you start writing the log. Okay, just like this one so far. And again, as I mentioned, you order all the writes by the timestamp and like by logical timestamp. I mean, they cited the Lamport. I mean, it's not the only one. I assume there should be some other logical timestamps. So any way of you can totally ordering all the writes. If you do that, then there wouldn't be any. There would be a lot of issues that you're asking will be solved. So talking about that, and then the main key, I mean, one of the things that they mentioned about the tentative. So all the writes will be tentative at first till they will be confirmed, right? So the point is, the main, basically thing that I need to highlight here, okay, is the log at each node holds the truth. Actually, the database is just the optimization of that truth, because at the end, log of those log are telling you the truth. Okay, database is basically a way to represent that, because you remember at some point those writes might, the writes will sit in the log until they become like confirmed. Yeah, I mentioned about this, Lamport clock, respect causality. And also, this is important, the causality of events, because, for example, like this example, okay, just just think about this example. You have this logical clock here, two logical clock. A has for meeting M1 at 10 a.m., else 11 a.m. And B is in this event is like in the machine B, let's say, it asks you to delete, update this one. But it has a smaller local clock. So with Lamport clock, this won't be this, okay? This clock should be bigger than this, right? Because we are totally ordering the events. So when A sends this, it includes this clock. When B receives this one, okay, here, it updates its clock to T prime, let's say. And when B create the delete action here, it timestamps it with it timestamp this action with this, which is bigger than T prime. So basically, this will be the order of the event at the end. You receive, you update your clock, you make the action, you put the timestamp. So the whole idea is Lamport clock respect causality as well, because it's important, causality of the events in the database or in the log. And what if A and B are concurrent? Of course, we already talked about it. Lamport clock provide total ordering of the events, right? Another thing that, I mean, so far, like I was supposed to talk about tentative right and like confirm right, let's say. So we're saying like, if we just follow that, okay, timestamp for right ordering, then there would be, you never know, maybe like, for example, at the moment, I have this computer that haven't really used last 6 months, I didn't even turn it on. So what if the last time before I turn it off, I updated file before it starts syncing, I just turn it off. After 6 months, now I'm turning it on, okay? So imagine that that write that I just now connected and trying to synchronize comes, you want to come inside, right? You want to come because it has a smaller Lamport clock. So you have to come, and then you have to re-execute all the logs that it was there, right? If you just consider this. So of course this will be an issue because it means you're never going to get rid of the log, okay? Because all of those writes will be tentative forever. So when you're going to basically confirm them, the tentative write. So the idea was that's basically a main replica. I'm talking about replicated databases. So the main replica or the main server or the central server will decide on the commit rights or decide on these certain rights are committed. So you have this commit sequence number that you can attach to the local timestamps, okay, and with the node ID and send it. So basically, this will give you the Lamport clock, and then you assign commit sequence number, okay. Then I mean, here I wanted to show you that you can get disagreement on different writes, okay? On different write after the synchronization, the two different replica can end up being disagree. That's why you assign one of them, one replica as primary or server, main server, or however you call it. If you follow that at the end, all the system should be synced with the server, or this is the one, basically is the actual tentative rights. Not actual, the committed rights. That's why you can start trimming the log. You don't need to keep the logs forever. As long as you have this committed, this certain log, you can get rid of all the logs before that last commit, because you have already a committed log. You don't need to keep the log forever. What else? Of course. course, and we talked about Lamport clock total ordering. So this was supposed to be my last slides. So is eventual consistency a useful idea? Of course it is, as they highlighted. Are update conflicts are a real problem? Yes, they are. All systems have some more or less awkward solution, like the one I show you about the Dropbox or the one Pedro was talking about Git. So they already talked about it. The complexity is warranted. So it is only tolerable if humans are the main consumers, okay? Otherwise, you can sync through a central server. If we are not dealing with the human as a consumer, and we are just talking about the servers talking to each other, a lot of problem will be dealt with, because talking about that, then you can consider the connectivity as like secure, more or less, okay? So you can assign all those things to a central server, so you don't need to do a lot of complication there. So one of the takeaway ideas, they mentioned eventual consistency basically. Eventually, if updates stop, all replicas are the same, okay? So you have the update function for automatic application-driven conflict resolution. Ordered update log is the real truth, not the database, because that's the one at the end will be start being the committed rights, right? The order log that they keep, the server, the main replica keeps, will be the real truth, not the database, because database can change, right? And we use application of Lamport clock for eventual consistency that respect causality through totally ordered events and to respect the causality. So those were the points I want to talk. We covered most of it. So any question about this? No?
Yes, I have a question.
Go ahead.
In the previous slide, you mentioned that, for example, if the dimensional consistency is achieved, all of the replicas are the same, right? So is there any benefit of that? Because if at the end all replicas are the same, but they still have to check availability, for example, in the server, master server, then yeah, it is just, the question I think it would be, it is just to inform the user that eventual consistency is just for users to know the previous data, the previous, for example, if you are trying to schedule a room or something, just information to the user. I'm sorry about
it. That's okay. But talking about why it's useful, it is useful. I mean, you're using Git, you have to use Git now, even if not now, but it's useful because they mentioned, and I said, because we don't have perfect connectivity. So at the end, I want all my data to be consistent. So no matter what services I'm using. I mean, maybe it's not clearly answering your question there, but I mean, if your question is about why it's useful, is that?
Yeah, the question is if all the servers have like eventual consistency, they still have to go to the master server, right?
No, no, you don't.
Oh, okay.
I mean, you don't need always. I mean, at the end, I mean, that's the idea. I mean, I'm having this Dropbox right here. It's synchronized now. If I start turning on my Wi-Fi's, because it's have a lot of problem with my Wi-Fi because I'm using Total Play, and it sucks. Okay, really. Like last night, like it was 2 a.m. and it just went. I mean, my signal went off. Okay, and I assumed they thought maybe no one is using 2 a.m. who's using internet. So I'm working on my Dropbox. I'm working on the files that I'm writing. Okay, but at the end, I want the data that I have in my local computer will be synchronized with the data I have in cloud. And then when I'm traveling, I want to access them in my phone. So I want all of them to be consistent. But eventually, so it's not about like, we're going to later talk about a strong consistency, okay? Which is like one level higher than eventual consistency. But that is very useful for me, right? Maybe I'm traveling in the flight. I mean, you see that a lot. I mean, I'm pretty sure you noticed. I can turn up all my data in my computer. I can edit like 1 year plan in my Google Calendar, and when I connect to the internet, it's synchronized with my Google account, right?
But you're talking to the master, right?
Huh?
But when you are synchronizing to internet, you're talking to the master.
Okay, so you want to say, for example, there is the Google server considered as a master, right?
Yeah.
But no one else is writing that, right? Maybe I'm writing my calendar. Some other students are booking some time with me to have talk. Okay, so we are all editing it. So if you want to say who is the master here? Yeah, that's a good question. But it's not about.
Can I?
Oh, go ahead.
Jump in?
Yeah, sure.
So the question that Luis is asking is, what are the benefits to have replicas or the other servers? Yeah, one could be you always want accessibility to your files or to your records or whatever. So you probably will go always to your replica next to you, and then if that fails, you go to the next one. I mean, if that fails, you go to the next one. So eventually you want consistency across all the multiple replicas. So that would be one, like availability. So if one data center fails, you have another one, and that's just one. But there are others. But I don't know if that kind of answers your questions. In terms of who's the master and who's the replica, that would be complicated to answer in terms of Git or Dropbox, because I'm pretty sure that there are more than one master.
I mean, okay, here, for example, about the Google Calendar, Google and things, I mean, it's not like, for example, the server will ever reject my update, right? It's the idea, for example, you're seeing my calendar, maybe I'm sharing with you, you can see my calendar. You can also put some events there. I can also put my events there, right? If there is any conflict between our events, okay, then it becomes like an application-specific conflict. If it's calendar, anyway, we have to sort out a way to resolve that conflict. But it's not about saying, okay, no matter I'm putting any events here, it's Google server going to decide whether to confirm or to commit those right or not. That's not the case, right? I'm editing my calendar, it will be committed. Unless there is a conflict with me editing it, you editing it, it's a shared calendar, then that would be basically, okay, I got the answer. Then that would be the time for, let's say, for example, which one of us gets synchronized first with the calendar, get a lower logical clock, get the higher basically priority, let's say. Then my event going to become basically faster than your event, because I get a basically lower sequence number, let's say, than your event. But they will be at the end, they will be all committed, right? I will see the events, and you will see the events. So talking about usability, it is useful. I mean, without a doubt. I mean, it's a lot. I mean, it's pretty much useful. I mean, without that, it would be a lot of issues. But of course, it's not. I mean, that's not just enough. It's not like, say, okay, we have eventual consistency. We don't need anything better than that.
Okay, yeah, yeah, I think it answers the question. It was just a matter just to confirm that, for example, at some point, a server can be itself a master, right? Because it fully knows that it is full updated, probably, and it doesn't have to go to check with a different server that it is fully updated or something.
Okay, yeah, true. Thank you. Did I? Oh.
I have a doubt.
Yeah, go ahead.
If the master replica fails or dies, is there a way that other replica takes the ownership, like master, or
honestly answering your question, I'm not sure if we have that description in the bio paper, but of course there is, and we're going to talk about that. How in this example, as just one scenario or one example, how that can happen and how we can solve or pick another like replica as a primary. Because for that one, I mean, having this distributed replica and having one of them as primary, it can solve a lot of issues, and we're going to use this concept a lot. And that's why we need to solve a way that, for example, the primary dies, now we have 10 servers without a primary, but there should be a consensus among them who will be the next primary.
Okay.
And we will discuss about that.
Okay, thanks.
So what I want to do now is I want to divide you to groups, and I have an update about the group 1 and group 3 already changed as recommended by Robert. I just changed it myself, okay, because I find out democracy doesn't work all the time, or it takes time to work, okay. So please check out, I'm going to divide you to the project groups, okay. So for like 15 minutes, okay, so you can talk with each other, exchange number, or do whatever you want, find a way to contact, to collaborate, or if you already did that, start talking about the state of the project, where you are at the moment, okay. It's clear? So
yeah.
So I'm going to do that manually because it's gonna take like 2-3 minutes time. So just bear with me. Okay, that's an issue. Okay.
I have a question.
Go ahead.
You explained something about CSN in bio, but I didn't understand how it goes. And also, when you explain an example with the graph, I didn't get it also.
It's just about like giving a sequence number for the committed rights, so everyone can keep track of that sequence number. So that's the basic idea. And the graph was about that's showing how the conflict can happen and how a primary can help to resolve the conflict.
Okay.
If you have more data, I can show you that, but I rather now do this division here. Or if you want to take like a 3 minutes break and come in 3 minutes, I'm going to be ready by then. Okay, because I'm putting you manually in one by one in the groups.
Okay.
And meanwhile, I'm here if anything.
Okay. One question. What about us, Alejandra and I? I mean, Ivan.
Yeah, I already assigned you another. I take one from the 4-person group. I put it in your group. So everyone will be 3
What
now.
is his name or her name?
In group 7, we are only 2 people.
Which one?
7.
No, no, we are talking about the
project.
Project.
Yeah.
You are 3.
One student has to left because I think he went to surgery.
Yeah.
For a medical condition.
Yeah. Antonio Rivera.
Yeah. Okay. Okay, so I mix. Okay, just don't move. Okay, let me fix everything. Oh gosh, Roberto. Okay, so Roberto went back to group 1. Group 1 is unchanged. I am going to merge group 2. No, group 3. Alejandro and Dorle with group 7. So you'll be 4. Okay. So please let me fix them. It's really difficult, I mean, trust me.
Is there a break right now?
Yeah, I'm going to take like 2 more minutes to divide you. Then I'm going to divide you in the rooms. At the moment I'm assigning. So it's gonna take 2 more minutes, 2-3 more minutes. So you can take 2-3 more minutes off, I mean, break.
Okay.
Charlie, what's your full name? I forgot, sorry.
Juan Carlos Díaz Castellano.
Okay, that's not even more trouble. I'm dividing you, okay? So please, if you fall in a wrong group, let me know, okay? Quit the groups and let me know. Come back to the main session, okay?
Okay.
Right.
Okay, Brian Campus. I'm searching to see your group members. So you are with Christian Alejandro, Jose Antonio Rivera.
Yeah, with Christian and Antonio.
So I said I merged you with Alejandro Andorle, right?
Yes.
Okay.
Hi, Maddie.
Hello.
I'm just.
Are you a member of our team?
No, I'm getting out. Just
Great.
no, wait. Oh gosh, I made a mistake. Wait.
That's sad.
Okay, so you're 4. Okay, it's correct.
Now we're 4. Yeah.
Yeah.
Did I do correctly?
Yes.
Yes. Thank you.
So it was your groups that you had a person that had surgery, right?
Yes.
Yes.
Yeah, we tried to contact him, and he answered that he was in the hospital.
Mm-hmm.
So.
Okay. Perfect.
Oh yes, Antonio told me. Well, I'm with him in the other assignment, and he told me that he's in the hospital. So yes.
Who?
Antonio is in the hospital, and Sergey, it's not going to be in the class anymore.
Yeah, true. So it's fine right now, right? So yeah, just the idea is please just make sure you know how to contact each other, and next week is the deadline, okay? So sort it out, okay. Okay, I'm leaving.
Yeah, Maddie, one quick question.
Yeah.
Can we book you for a quick meeting on, depends on your availability, but
Yeah.
just to go through the document that you sent us and just to be sure of what we need to make for deliverable?
You mean for the project or for in general?
For the project, just to make sure that we understood correctly all the
The
things that you
deliverable,
mentioned.
I said it's not, I'm not gonna check. I'm sorry, it's not, I'm not gonna have time even to go through your code. So
No. I mean, it mentions that we need to run some tools like the lint and the go.
I mean, as long as you followed it, okay, and you show me that you finish it, that's it. And then the rest would be just talking about the experience. I mean, I want to hear which one was the part, like the difficulties that you faced, what was the easy part, how you solved the difficulties, you know?
Okay.
Yeah, that's the idea.
Like a presentation?
Okay. Pardon?
Like when we're going to present what we did, and
you don't need to prepare any file for presentation. You can just go walk through the codes and like talk about it, okay? Or just show it, have it as a background, and then talk about your experience while you're showing it or running it.
Okay.
But no need for PowerPoint or anything, no.
You will pick some of us, and
no, I want all of you to talk about it.
Okay.
But it's not like you have to talk like 2 minutes. But I want to make sure basically you did it together.
Okay.
But at the end, at least you understood the solution, because I know some people are better, some people are not that good in programming, but at least understanding the solutions.
Okay.
Okay, great.
I'm leaving.
Thanks.
So you can try to see.
Bye.
Bye.
Sámalo.
Ah,
Te paso esa cosa por el chat ahí.
Guys, sorry, I'm interrupting. I just want to make sure everything is working fine.
All good here.
Yep.
Okay, I did it correctly then. Okay, perfect.
Thank you.
Hearing out.
Thank you.
Yo pensaba que el hi, Maddie.
Sorry guys, I'm just checking to make sure things are fine and I did it correctly.
Yeah.
Yes, you did.
Yeah,
All
you
good?
did.
Yeah, this is all good. Yeah.
Okay, just make sure you know how to contact and communicate. And
Yeah,
we were in contact before.
okay, perfect. So you have the you already have the repository.
Yeah, I did it a while ago.
Okay. I'm leaving the room. Bye.
See you.
Hello.
Sorry again, I jumped.
Hey, Madi.
Just to tell you, you haven't made the repository in GitHub yet.
Yeah, we have a repository. I send you the mail confirmation today at morning.
It's like you have a group tree, right?
Yes.
No, it's not. I mean, let me share with you my screen so you know what I mean.
Yeah,
Like,
I had accepted the email invitation, but I'm not sure if I.
Like this. So you put the code of the class and then your group number in the organization. You can create this, okay? So the whole idea is I want to have a copy in my organization. So like if I have group 1, 2, 3 missing, 4, then 5, and 7 or so missing. 7 is already diminished, so 1 and 3 are missing. 3 and 5.
Okay, and our teammates the 3, right?
Yes, group 3, right.
Okay.
Okay. I'm leaving.
So, okay.
Yeah, question?